Huh?
She just didn't even do it.
Did you just start the recording?
I just started the recording.
Jeanette is trash.
Hey, none of that kind of language. All right. So let's start exercises 1.1. Number 1.
A.
False. What was the question? Yeah, I need to pull out my book.
It was,
Are the irrationals inductive? Is that what it was?
yeah, maybe. Because I said false because one, you need to have one in an inductive set.
Let's see.
It was the set of irrational numbers is inductive.
Number 1 was the set of irrational numbers is inductive. Right. That's false. Why is that false?
That's false because you need at least one.
Because 1 is rational. Therefore, it's not irrational. And so 1 is not in the irrational.
That's all I have to say.
That's a good enough explanation for me.
I wrote.
Explain it so you understand it.
I wrote 4 sentences.
All right. B. What did you get for B?
False.
False
Okay,
because
so
it does not
first of all,
include
the
natural set.
set of squares is rational, or the set of squares of rational numbers is inductive.
The set of squares of rational numbers. Right.
Yeah.
So we know that 1 plus 1 is equal to 2 is in the naturals, right? 1's in the naturals, and 1 plus anything is also in the naturals. So we know 1 plus 1 equal to 2 is in the rationals, but square root of 2 is not in Q. So this is a square of a number. That's the square of that.
Oh yeah.
This has to be in every inductive set, but the square root of 2 is not irrational. So I can't take rational numbers, square it, and get 2. 2 is in every inductive set. The squares of the rationals would have to include 2, but the square that gives you 2 is the square root of 2, which is irrational, not rational. Does that make sense?
Yeah.
All right, what was C?
The sum of irrational numbers is irrational.
The sum of irrational numbers is irrational. False. Square root of 2 plus negative square root of 2 is equal to 0. It is rational.
Oopsie.
Right?
I said true.
But it's not true. It's false.
Wait, are we on C?
C.
I either read it wrong or my explanation is insane. The sum of rational numbers is rational. So you just have to calibrate one thing.
Yeah. You need to come up with one example where it's not true. Or else it's false.
I said true because square root of 2 plus square root of 2
Donnie,
is
you
rational.
That's just an example where it works.
The sum of irrational numbers
Well, how am I going to
is
go through
irrational.
every single
Right.
case?
So here's a sum of irrational numbers. Is it rational? No.
No.
Or is it irrational? No, it's rational. So the sum of irrational numbers is not necessarily irrational.
What do you want me to do on my homework? Correct it? Or
Sure,
mark
correct
it wrong?
No, you don't need mark. D. What does D say?
The product of irrational numbers is irrational.
The product of irrational numbers is irrational. And this
False.
one's false?
Wait, I said
False.
false.
Square root of 2 times square root of 2 is equal to 2 is in Q.
Contradiction.
So there's a product of irrational numbers and it gives you irrational.
Yeah.
This isn't proof by contradiction, it's proof by a counterexample.
Counter.
Yes. Alright. And then E, what does E say?
It says, if n is a natural number and n squared is odd, then n is odd.
And is that true?
Yes.
No, that's false.
True.
It's false.
No, we already proved that.
If n is a natural number and n squared is odd, then n is odd.
We proved that A squared is odd implies A is odd last time.
No, we did not.
Yes, we did.
A squared is never odd if A is odd. Period.
What's 3 squared?
Yeah, it's 9.
Brett? I don't know why I did that.
Alright, so that was number 1, right?
Yeah.
Wow, that was hard. Let's move on to number 2.
I got 2 of those.
Number 2A, what does it say?
It says,
Wait, Donnie, you didn't explain. Do you need to?
I don't remember what it said now.
It says if it's odd and it's e squared, it's
Oh, you don't need to prove it.
because that's a theorem, or that's a.
I proved it in class last time. That wasn't a theorem, I just proved it because I thought we were going to use it, and we didn't use it. We just used the fact that a squared is even implies a is even.
Right.
So, I didn't need to prove it, but we did prove it. So, we already know that's true.
so the second one is, second A is every non-empty set of real numbers that is bounded above has the largest member.
Is that true?
It's false.
It's false.
How do you know?
Because if it's not inclusive on the greater than or equal to sign.
Yeah, so you were probably thinking the interval 0, 1, something like that. Let's see what I wrote there. Oh, you don't know notation yet. I wrote this.
Okay.
That shorthand for plug in 1, plug in 2, plug in 3, plug in 4, plug in 5. So this contains, this is a set. Well, really it's a function, but we think of it just output as a set. 1 over 2, 2 over 3, 3 over 4, dot, dot, dot. So it's matched, or it's bounded by the number 1. 1 is always greater than this. But you can't pick a number smaller than 1 that I would eventually get bigger than.
But that one works, right?
This one also works.
You can't pick a number smaller than
You
1.
can't pick a number smaller than 1,
Yeah, I can find a smaller number. Or
that we can't find a bigger number between it and 1. This one's a little bit hard to argue. This one you can prove directly. But you don't really know how to prove that directly yet, so this is perfectly fine. Let's see, what does B say?
If S is a non-empty set of the positive real numbers, then 0 is less than or equal to inferior S.
The infimum.
Infimum S.
So we have S is a subset of the positive real numbers. Is it true that 0 is less than or equal to the infimum of S?
Yeah.
And yes, that's true. 0 is always a lower bound of any set of positive real numbers. And therefore the infimum, or the greatest lower bound, has to be greater than or equal to every lower bound. Right? So that one's true. C.
Okay, real quick, I want you to screw up on the subset. Like, if S is a subset of R, or of the rationals, that's what R is, right? Rationals.
No. R is the real numbers.
Or the, what about Q?
Q is rationals.
Oh, okay.
So all the real numbers that aren't rational is what we mean by the irrational.
Right.
So if you want to represent the irrational numbers using sets, it would be the set of R minus the set Q. Take everything in R, get rid of everything that's in Q. Now you have the
Okay,
irrational.
so my question was, for us to say there's a set S that is a subset of all the real numbers, meaning that is saying everything in S is also in R, but not everything in R is also in S.
Correct.
So, like, S could literally be 26 and 4. That could be the set. And
Correct. Basically, the way you're saying S is a set where all its elements are positive real numbers. And it's specified a non-empty set. I didn't write that up there. Because only non-empty sets can be bounded, right? Doesn't make sense to bound an empty set. Alright, what does C say?
If S is a set of real numbers that is bounded above, and B is a non-empty set, subset of S, then the supremum B is less than or equal to the supremum S.
So it said if S is a set of R. That means S is R. Does that not?
S is a subset of R.
It has 6 subsets.
It's a set of real numbers. Which means everything in S is a real number.
Okay.
Which means everything in S is also in R, which means S is a subset of R.
Well, also means R is a subset of S.
No, it does not.
Because S is. Okay, you're right.
think about it this way. The students in this classroom are a set of people. That doesn't mean every person in this classroom.
Is a student.
Look at this set of people. Look at this group of people. We are a subset of the people on planet Earth. Because everyone in here is a person.
Right.
Okay. Everything in here is a real number, a set of real numbers.
If S is a real number.
So S is a non-empty subset of R bounded from above. B is a non-empty subset of S bound. Just B is a non-empty subset of S. Is it true that the supremum of B is less than or equal to the supremum of S?
Yes.
Yes, that one's true. And you can prove it pretty easily if you wanted to. Right?
Oh.
You take the supremum of this, which is, call whatever you want. What does it mean to be the supremum of C? That means C is greater than or equal to, for all x in S. X is less than or equal to C is less than or equal to B, where B is the bound.
And the B is also equal to the supremum.
No. B is any bound. Say I've got the set 0, 1. What's the supremum of that set? 1. What's the upper bound of that set? 29, 52, 8,564. B is any upper bound. So I've got S as a subset of R, B is its upper bound.
All right.
Right? And then since everything in B is also in S, right? Then if B is greater than everything in S, B is greater than everything in B. And so we have C is the supremum.
Between B and any number in S.
C is the supremum of S, which means C is greater than or equal to anything in S, which means it's greater than or equal to anything in B.
Right.
Because everything in B is in S. So C is an upper bound of B.
Right.
So the infimum of B, its least upper bound, is less than or equal to every upper bound. So if this thing's supremum is an upper bound of this, then this thing's supremum
Has to be lower.
has to be less than or equal to it. Does that make sense? The infimum, or the supremum of this, is an upper bound of this. And therefore the supremum of this is less than or equal to the supremum of this.
Yeah.
Because the supremum is less than or equal to any upper bound. That's what the supremum is. It's the least upper bound.
Right.
That make sense?
Yeah.
So, that was kind of messy writing that in there, but I think you can prove it. It's not hard to prove. And we probably did prove real similar to that, right? Okay, what's number 3?
Use the principle of induction to prove that with a natural number n and its summation of a squared equal to the equation of a squared. Equal to the equation of the summation of a squared.
Okay, so we're doing prove that the sum k, or I guess I use a j, don't I? So I can use k marker. J equal to 1 of j squared all the way up to n is equal to, let's see, squared, what is that?
It's n times n plus 1 plus
2 n plus 1
Yeah.
over 3?
6.
6. Thank you. Prove that that is true for all n in n. Right?
Yeah.
Beginning natural number you want, if you add up the squares of the natural numbers up to that number, it's going to equal this. That make sense?
Yeah. So first you can do is see if 1 is true.
1. Let A equal the set of all x in n such that that is true. Right?
Wouldn't it be n and n?
Why is that necessary, by the way?
As you get more comfortable with proof by induction, you'll stop doing this. This is just being very clear about what exactly we're saying. We're saying let A be the set of everything that makes this true. You use proof by induction to show that A is the set of all natural numbers.
Okay.
So this line, what we're making here real quick is A is a subset of natural numbers and A satisfies that. That's what this is saying. the next thing that we're going to show is that A is inductive. So it's one of the first statements we did. If
it's inductive, it's natural.
A subset of natural numbers is inductive, it is a set of all natural numbers. It's one of the first things we did. So we use the fact that A is a subset of n, satisfying this. Then we show A is inductive, which implies n is a subset of A. Right? What was our definition for the natural numbers?
If A is inductive, that implies
the natural numbers are the intersection of all inductive sets. Which means the natural numbers are in all inductive sets. Which means every element of the natural numbers is in every single inductive set. So if A is inductive, then every element of n is in A. Right? In our top line, we said every element of A is in n. So if A is a subset of n and n is a subset of A, then A equals n. That's what we mean when we say two sets are equal. They're subsets of each other.
Thus, we prove that every number in the natural
Then
numbers
we show that A, the set of all natural numbers that makes this true, is all natural numbers. In other words, we show this statement is true for all natural numbers.
Okay.
That's the logic.
Okay, thank you.
And as we go through it, we kind of stop using this A. We kind of talk about behind the scenes. We say, look, this statement's always true for 1. If it's true for k, it's also true for k plus 1, therefore it's true for all n. And we kind of ignore the A as we get more comfortable with it. But that's out of laziness and assuming that your reader follows that. So as you begin proof by induction, it's good to explicitly write out what exactly the logic is and make sure you keep track of that. And then once you get comfortable with proofs in general, you start to leave stuff out, and that's perfectly acceptable. Alright, so A is a set of all natural numbers that makes that statement true. 2. Observe
One words.
that the sum from j equals 1 of j is squared to 1 is equal to 1 squared is equal to 1 is equal to 1 times 2 times 3 over 6.
Is equal to what?
Comma. So that, get rid of this now.
Observe so that.
Observe that this is true, so that 1 is in A, or showing that 1 is in A.
Yeah, that's fine. Okay.
Okay. Judy. Gracie doesn't want to be outside. Okay, so next, what do we do? Remember, to show us the set is inductive, 1, so if I want to show A is inductive, first what I need to show? I need to show that 1 is in A. 2, I need to show K in A implies K plus 1 is in A.
Okay, so this implied statement is saying
If K is in A, then K plus 1 is in A.
okay.
If this, then this.
Okay.
How do we prove if-then statements? We assume this and show that leads to this. How do I show that an even plus an even is an even? I say assume x and y are even, and then you show x plus y is even. So you assume your condition and you show it leads to conclusion.
Okay.
Does that make sense?
Yeah.
So we did this, now we're going to do this. You can almost view it like a separate proof. Prove that if k is in A, then k plus 1 is in A.
Okay.
So 3. Assume or let k in A, however you want to do it. But I usually like to start with assume.
I like
Okay,
it.
it's common in the proof by induction. Assume k is in A, and k in A implies what?
That k plus 1 is in A.
Yeah, no.
Oh, sorry. K.
What does it mean for k to be in A?
It can replace every n.
That k satisfies the statement. A is a set of all natural numbers that make the statement true. Assume that k is in A. Or in other words, assume k makes that statement true. So we're assuming that the sum from j equals 1 of j squared to k is equal to k times k plus 1 times 2k plus 1 over 6.
Yeah.
You understand that assumption?
Yeah.
You see how it's helping us prove this?
Yeah.
Assume k is an a. Now we need to show that implies k plus 1 is an a. Now, it's often helpful when you're doing a proof by induction to see where you're trying to get. What maybe we'll do like what I sometimes do in the past.
The bottom line.
The bottom line, our bottom line is, therefore,
K plus 1.
A is inductive, right? And you can now see how that means A is equal to N. So that finishes the proof, and you understand that, right? Showing that A is inductive is equivalent to showing that K plus 1 is an A, right? Right? What does it mean for K plus 1 to be an A?
The statement.
Then the sum from J equals 1 of J squared to K plus 1 is equal to K plus 1, K plus 2. And don't screw with algebra on here. When you plug in K plus 1 there, you're going to get 2K plus 3. You see that?
Oh no! I thought you didn't do it that way. I thought you did it this way. I thought you did K and then you added K plus 1 at the end. Plus K plus 1.
Look, watch. What's going to happen is he's going to times that net.
I know how he's algebraically going to get it. I thought you wrote it like this though. I thought you wrote this one right here, and then you wrote plus K plus 1.
Times.
Well, we'll get there. But ultimately, this is what it means for K plus 1 to be an A. Just like this is what it meant for K to be an A, this is what it means for K plus 1 to be an A.
Okay.
So now my ultimate goal is to show that this being true implies this is true.
Okay.
So I need to use this to prove this.
Yep.
The only way to do that, this is the sum of 1 squared plus 2 squared plus 3 squared all the way up to k squared. This is the sum of 1 squared plus 2 squared plus 3 squared all the way up to k plus 1 squared. Right? So I need to add k plus 1 squared to both sides.
Oh, add?
What is this? Remember.
I think that's where I got.
Yeah, so let's write to the side for a second. If I'm doing the sum from j equals 1 of j squared to 5, have I been losing my squares? No, I have them all there?
Yep.
Okay. If I'm doing this, what is this equal to? This is equal to 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared, right?
Yeah.
Pretend k is 5 for a second. Then k plus 1, j equals 1 j squared of k plus 1, or 5 plus 1, is equal to 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus k plus 1 squared. That's what this is.
Right.
And I can rewrite that as, I can write it this way. J equal to 1 j squared up to 5 plus 5 plus 1 squared. Right? So if I take this and I add that to it, I get this.
Right.
Same thinking. I take this, add k plus 1 squared to this, that gives me this. See that logic? What did I do to one side? I got to do to the other side. So I need to add that to both sides. Then, adding k plus 1 squared to both sides, I might take the time to write that out, but we'll just skip straight to it. Then the sum from j equals 1 of j squared to k plus 1 is equal to k plus 1, 2k plus 1, all over 6, plus k plus 1 squared. Right? Added k plus 1 to both sides of k plus 1 squared to both sides of this equation. That gets me here. Now I just need to algebraically manipulate this side until it looks like this.
Yeah.
Right? So first thing I'm going to do, I'm going to get this over a common denominator 6. Right? And I'm going to also factor out a k plus 1 from both terms. Can you follow that in one go?
Yeah.
Maybe I'll do 2. K plus 1, 2k plus 1, plus 6, k plus 1 squared, over 6. Good?
Yeah.
Which is equal to,
K plus 1 times.
now I'm going to factor out my k plus 1. So it's equal to k plus 1 times, when I pull out my k plus 1 from here, what do I have left? I have 2k squared plus k. You see that? Okay.
2k squared.
Uh-huh. So I pull out my k plus 1, which gets rid of this term, and I still have my k times 2k plus 1. What's k times 2k?
2k squared.
What's k times plus 1?
Okay.
Good? And we also need to distribute, remember I'm pulling out 1k plus 1. I factor out 1k plus 1 from both of them, so there's still 1k plus 1. So 6 times k plus 6 times 1. See all that? You can take a couple more steps to do that algebra if you need to, but you should have ultimately gotten there. And now, look at where I'm at, look at where I'm trying to go. I've got k plus 1, 6, 6. This is k plus 2, 2k plus 3. Could I refactor this way?
Definitely. Because it's really 7.
Right, I can. K plus 1.
You need 7k.
I'm going to do it different than this because usually we think about, I need a 2k term and a k term, right?
Right.
That's how we usually think about it. And let's see, the numbers here need to add to be 6. And then this number times this number plus this number times this number need to be 7. Because we have 7 k's in here. So I know what gives me 6. 3 and 2. And I need to put the 3, so plus, plus. If I put the 3 here and the 2 here, that gives me 6k plus 2k is 8k, so that doesn't work. So if I put the 3 here and the 2 here, 2 times 2k is 4k, 3 times k is 7k. So we get 7k all over 6. And we're done.
Yeah, crap's actually fun.
Oh, proof by induction is kind of fun. It's one of my favorite types of proofs to do.
We have another one in here.
You have a lot more proofs by induction. I intentionally chose a bunch of proofs by induction to try and hurry up and get you comfortable with this because proof by induction, when it comes up when you're trying to prove something and you can use proof by induction, that's a moment where you're like, oh, phew. So you got to get past where these things are scary to the point where you're like, I hope I can use proof by induction to prove this.
And the whole idea of proof by induction is proving that the set of numbers you're using is inductive.
The set of numbers that some statement is true for, as is the natural numbers. Is that working okay?
Yeah. Is the natural numbers.
Yeah, or some subset of the natural numbers. Sometimes it might not be true for 1, and it might be true from 2 onward or something like that. But I'm sure we'll see examples of that. Anyways, does this proof make perfect sense?
Yeah, it does.
Alright, let's move on to the next one. What's the next one?
The next one is number 4.
Want to read it to me?
Let n be a natural number and find the formula of that. The summation
Yeah, I'll show it
j times j plus 1.
So we're looking for, so let n, I think I understood it. In
to
n,
you. 1 cubed series.
find formula for the sum from j equals 1 to n of j times j plus 1. Is that what you said?
Yeah.
It's not?
Oh, I'm looking at the one. I'm looking at 5 and 4, sorry. Yeah.
Okay, so find a formula for this. Now, holy smokes, easy peasy. Pops right out at you.
It took us, I know, you can times it, but it took us forever to figure that out.
So this is equal to the sum from j equals 1 to n of,
Squared plus j.
make sure you apply these sums to the whole thing, j squared plus j.
That did not pop out at me.
Well, that's fine. Once you see it, it will probably pop out at you later. Which is equal to, now you can split that into two sums.
J squared sum of j.
The sum from j equals 1 to n of j squared plus the sum from j equals 1 to n of j, which is equal to n times n plus 1 times 2n plus 1 over 6 plus n times n plus 1 over 2.
There's your formula.
And there's your formula. You could put it together. I mean,
We did. I made it a lot more simpler than that.
yeah, that's kind of a lazy formula, so let's keep messing with it. Which is equal to, multiply the right-hand one, top and bottom, by 3.
Then you can factor out n plus 1.
Yep, n plus 1, 2n plus 1,
Plus 3.
plus 3n, n plus 1, all over 6, right? Factor out the n and the n plus 1, which gives us n times n plus 1 times n times n plus 1 is what we're factoring out, right?
Yeah. So
Which gives us 2n plus 4.
You're factoring out n plus 1.
All over 6.
Or you're factoring out.
Factor out n and n plus 1, right? On this term, that leaves me 2n plus 1. And on this term, that leaves me 3. So I had x times y times z plus
I see,
3
I see.
times x times y is equal to x times y times z plus 3.
Yeah.
Good? And then we can factor 2 out of this and cancel it out the bottom. So it gives us n times n plus 1 times n plus 2 all over 3.
Yeah.
Not a bad little formula. Okay, any questions on that one?
If you know how long it took us to do that, we sat there and we're like,
But when you figured it out, when you made this leap, how awesome was that?
it was easy.
That instead of this new complex piece that you didn't know how to handle, you split it into these two simple pieces that you already figured it out for. That's a great leap. And that kind of manipulation is another thing you're going to want to get comfortable with in this class. Because a lot of, when we get to integrals, a lot of it is you want to manipulate sums like this. Okay. That was number 4. All right, let's do number 5. What was number 5?
So this is the one you need to look at.
Say that again.
You need to look at this one. Unless I can explain it, but it's probably easier for you to look at. See it? It's the summation.
Prove that the sum of j cubed is equal to the sum of j all squared. Okay. Oh, this is one we did last week, huh? After school. You me?
Me and you did it, yeah.
Yeah, I missed this one. Or I did it. Is it illegal for me to look up online what is equal to the summation of j cubed?
No, feel free to use online help. Feel free to use whatever you want. I just want you to have a valid proof when it's all said and done.
Well, I just said j cubed equals this, and then I made my other side look exactly like that.
Oh, no, you can't do that.
What?
You looked up a formula for what this is, and then showed that this equals that. You know the formula for this already, and then you show that this equals that. You did it backwards.
I know I did it backwards, but
No, that is not valid. You cannot use information on the internet to just, because, I mean, you already know this is true. That's almost like referencing the book to prove it.
yeah.
It's like, notice from problem this, that the author's having me prove this, thus it is true. Because the author would have me prove it if it wasn't.
Okay.
I looked up on the internet and they said, yes, it's true.
No, they said this is what it equals, they said.
Right. How did they know that that's what it equals?
Because they proved it.
Right. There's a proof there. So I'm fine with you looking up information, that's great. How about with you looking up proofs, that's great. And understanding their proofs and then writing your own proof. Just make sure when it's all said and done, you proved it. That's all I want.
Okay.
And so no, what you did doesn't count as proof.
Okay, we have to read it.
That's fine. Alright. So, 1, again will be a little tedious and write A. Let A equal the set of all n in n such that that is true. Right?
Mm-hmm.
2. Observe that the sum from j equals 1 of j cubed to 1 is equal to 1 cubed is equal to 1 is equal to 1 squared is equal to the sum from j equals 1 j to 1 squared, showing that 1 is in A. Good with that?
Yeah.
Now what do we do? How do we show a set is inductive?
See that
You
one?
first show that one's in there, then assume K's in there and prove that.
Implies K plus 1 is. Perfect. Assume K is in A. Or in other words, that the sum from j equals 1 of j cubed to k is equal to the sum from j equals 1 to k of j all squared. Right? That's what it means to assume k is an A. But you can do the same thing we did before. Come down to the bottom. Therefore, A is inductive. How do we know that A is inductive? We'll know A is inductive when we know that K plus 1 is in A. How will we know when K plus 1 is in A? We'll know that when we know that the sum from J equals 1 of J cubed to K plus 1 is equal to the sum J equals 1 to K of J all squared. Right?
Let me see. Yeah.
Again.
Okay, so we're making.
Oh, oops, K plus 1.
Yeah, I was. Wait, no. Aren't we supposed to only manipulate one side of this equation?
Before you think about what you're supposed to do, just think about the logic of what has to be done overall. You're going to assume that K is an A.
Yeah.
You're going to show that leads to K plus 1 is an A.
Uh-huh.
What does it mean for K plus 1 to be an A? It means K plus 1 satisfies this statement,
Yeah.
which is exactly what this says.
Okay.
Okay. So we've got this. We know we need to get here and we're done. So we got to get from here to here. Now, one obvious thing to be thinking in your head is, well, this has K plus 1 cubed. This doesn't. So if I add K plus 1 cubed to this, then that makes this look like this, right? Now the whole hard part is showing that leads to this looking like this.
Okay, my problem with this is last time when we were proving we did plus K, like you said we can do K plus 1 cubed, we can just add it to J. Only with our other one, it was this summation equals this formula. This one is just this summation and we don't have a formula, so we can't add K plus 1.
But what is this?
I know that one.
So use it!
Okay, so yeah.
We already proved what this is.
Yeah, but you said, right, I already know that one. So we're not messing with the left-hand side.
Well, we are a little bit, because we need to add K plus 1 cubed to it.
Okay, let's see how this.
We need to make the left-hand side look like this. Same thing we always do. To go from this to this, what do we need to do? Add K plus 1 cubed.
Right.
So we need to add K plus 1 cubed to this. But first let's get this in a more reworkable
K
form.
plus 1 squared.
So then the sum from J equals 1 to K of J cubed is equal to K times K plus 1 over 2 squared. We already know what that is. The sum of that is that. We already proved that.
Yeah.
I mean, maybe make some side notes real quick. Here's what we've already proved.
We have.
We proved that the sum from j equals 1 of j to n is equal to n times n plus 1 over 2 for all n in n. We showed that. We showed that the sum j equals 1 of j squared is equal to n times n plus 1 times 2n plus 1 over 3 over 6 over 6 for all n and n.
We don't need that though.
I know we don't need it, but the point is from here on out we can reference these things.
I know. Okay, listen.
So that sum is lying exactly right there. So I know what that sum is. It's this. So that sum is that.
Yeah.
Is there any question about that?
Nope.
No.
Now simplify a little bit. It's equal to k squared, k plus 1 squared over 4. Right?
Mm-hmm.
Okay. Now, since we see that trick, let's see what it's going to look like down here when we have it all said and done. So that we can see exactly where we're trying to get. We're trying to get to k plus 1, k plus 2, all over 2 squared. Right?
Oh, yes.
That's what this is. Just like that's what this, just like that's what this is.
Right.
That to that, same thing as that to that.
Yes.
Right?
100% get you.
And we can even unwrap this a little bit more if we want. That helps us think. Okay. So now, it's almost exactly like every other problem. We have the sum of the cubes is this formula for k. Show that the sum of the cubes is this formula for k plus 1. So now I need to add k plus 1 cubed to both sides. 5. Adding k plus 1 cubed, we get that the sum from j equals 1 of the cubes to k plus 1 is equal to
Okay. So I have a problem with it.
You have a problem with it?
Because it seems like
I took this equation right here.
I see what you did.
That equals this.
Why do you
And
know
I
that?
added
I
k
thought
plus
we're
1
trying to
cubed to
prove
both
that.
sides.
I thought we're trying to prove that. Because don't you prove it once you show that the inductive set works?
We need to show, there's two things we need to show. We need to show 1 is an A. We need to show if
Okay.
k is in A, then k plus 1 is in A. What does it mean for k to be in A? K to be in A means this, which means this. This is what it means for k to be in A.
totally understand now. Okay.
Okay, so we need to show that if k is in A, k plus 1 is in A. So I've got the sum of the cubes all the way up to k equals this. Then the sum of the cubes all the way up to k equals, or all the way up to k plus 1 is this. I added k plus 1 cubed to both sides. To go from this to this, I add k plus 1 cubed to both sides. You see that?
Yes.
You follow that? Alright, now we just need to algebraically manipulate this side.
Which is where that's not done.
So multiply top and bottom by 4 for this term, and factor k plus 1 squared out of both those. You with me? So I'm going to do a little bit of steps in one, make sure that they all make sense. So we're factoring out a k plus 1 squared. I'm multiplying top and bottom of this by 4. So from this term we still have a k squared. And then from this term we have a 4k plus 4. Did you follow that?
Yeah.
Okay. We've got k squared plus 4k plus 4. We need k plus 2 squared.
Oh, how convenient.
What are the odds?
This is so stupid.
I didn't write the bottom of our thing because I'm writing on paper. And I have a whiteboard.
Yeah, it makes a difference. Because you can't have blank lines on paper.
No, it looks so ugly.
You understand the proof?
Yeah, I should probably stop looking at the board and see if I can do it myself.
So I can erase it. Here goes the top line. You better hurry.
K plus
Yes, I could just go to the other board. Okay, what's the next problem?
Let m and n be natural numbers. Prove A, so A, prove the sum m plus n also is a natural number. Hint, fix m, define the set n to be the statement that n plus n is a natural number.
So prove that the sum of two natural numbers is a natural number. Is what we're doing, right?
Yeah.
1. Wait for Jacob's attention.
You want to see what
I
I
can
did?
finish this later.
That's okay. You can see what I did.
I'm done.
You're good?
Even know where to
Alright.
start.
Okay.
So this number is what?
6a.
6a.
Okay, prove that two natural numbers is natural. Oh, we're doing it by induction too?
Oh, yeah. Of course. Of course, of course, of course. These are all proof by nothing. Anytime you're proving something about the natural numbers, you're probably going to want to use induction. So make sure you understand how we're going to go about doing this. So we need to show that the sum of two natural numbers is a natural number.
Yeah.
Another way of saying that is, given a natural number, I can add any natural number to that I want, and I still have a natural number.
Okay, so we assume there's a natural number.
So, yeah, start out with some natural number. Doesn't matter what natural number it is. I'm going to say you can add any n to it you want, any natural number to it you want, and it's still going to be a natural number.
Yeah.
Now here's the logic of how my proof's going to flow. I'm going to say let m be any natural number, and let a be the set of all natural numbers that I can add to m and still get a natural number. And it's going to turn out that a is a set of all natural numbers. So given a natural number, I can add any natural number to it I want, and the result is a natural number.
Okay.
Therefore, the sum of natural numbers is a natural number. You see the overall logic there?
Yeah. I see.
Can you smell it too?
Yeah.
Smells like Expo. You still cranking away?
Where
Don't get so caught up in the notes you lose track of the logic.
is natural.
Because you have the notes on there forever. So let's make sure the logic makes sense, because you can't ask me questions when you watch the lecture later. So, what are we trying to show? We're trying to show that the sum of any two natural numbers is a natural number, right? Here's my logic for that. I'm saying, pick any natural number you want.
Okay.
Let A be the set of all natural numbers that I can add to that, where the result is still a natural number.
Okay.
I'm going to show that A is the natural numbers. So in other words, given a natural number, I can add any natural number to it I want, and the result's still a natural number. You see how showing that A is inductive finishes our proof?
Yeah.
Yeah.
Yeah, okay. So let's see, is A in there? Or is 1 in there?
Yeah. Because n plus, if n, let n be 1, right? And then n can be, the arrow means implies.
Yeah. So let's make sure we understand this. Remember that we proved that the natural numbers is inductive, right? What does it mean for the natural numbers to be inductive?
Plus that is also.
Two things. Yeah, 1's a natural number, and if k is a natural number, k plus 1's a natural number. If n's a natural number, n plus 1's a natural number. That's what it means for it to be inductive.
This is the first time we've done this. This is the first time we've used this rule. Oh no, we use it with k, don't we?
We use it all over.
Oh yeah, k.
So therefore, 1 is in A, right?
Hey, I did that exact same thing.
Wonderful! That's a perfect start. Because it's what I did. I know perfect.
Different.
Oh, proving that that set is inductive.
Yeah. So now, 4.
Wait, why do we know therefore 1's in it? Because
We just barely showed that m plus 1 is a natural number. Remember, A is a set of all natural numbers I can add to m and still get a natural number. Can I add 1 to m and get a natural number?
Yeah, therefore 1's in it.
Therefore, 1 is in A. A is a set of all natural numbers I can add to m, with the result being a natural number. Right now, I know that m's a natural number, which means m plus 1 is a natural number. That's what it means for 1 to be an A. For 1 plus m to be a natural number is what it means for 1 to be an A.
Because 1 is another natural number.
Because 1's a natural number, and A is a set of all natural numbers that I can add to m to get a natural number.
Okay, right.
Can I add 1 to m and get a natural number?
Yeah, therefore 1's in.
Yes, because m plus 1 is a natural number. Right? Showing that 1 is in A is the same thing as showing m plus 1 is a natural number.
Yeah.
Good? Alright. What's my next line?
Assume
Assume what?
K is in A.
Assume k is in A. What does it mean for k to be in A?
A number plus k is also a natural number.
n plus k is a natural number.
Is it n?
Oh, sorry. Thank you. That's what it means for k to be in A. I'm going to start using shorthand because I think you guys understand.
Yeah.
Right? Now, do we need to go right at the bottom and work our way up? Or is it obvious to you where to go?
I like when we do that.
Alright, then let's do that. Therefore, A is inductive, which is what we're ultimately trying to get to.
Then
How will we know that?
K plus 1 is
Then k plus 1 is in A. How will we know that? Then n plus k plus 1 is in A.
Okay.
Right?
K plus
A is a set of all numbers that I can add to m and still get a natural number.
Right.
Oh, sorry. I see your confusion. This was supposed to be an n. Sorry.
No, it should have been A.
No. If something's in A,
Alright,
that means when I add it to m, it's in the natural numbers.
Yeah.
A is a set of all natural numbers that I can add to m and still get a natural number.
Right.
Right?
Yeah.
Okay. So we understand this. So I need to show that m plus k plus 1 is a natural number. I know that m plus k is a natural number.
So now you need to show that n plus k plus 1 is a natural number.
How do I show that this is true if I know that this is true?
You make k plus 1 equal a, and then you do n plus a.
No.
No.
Wait, let me think about this.
What is n? It's a set of all natural numbers, right? Is it inductive?
Yeah.
What does it mean for n to be inductive?
That k plus 1 is.
If k is in it, then k plus 1's in it.
Well, what about n plus k is in it?
Same thing.
Then what?
So n plus k is in it.
Plus 1. Plus 1.
Oh!
Oh!
You can add
5. Since n is inductive, then m plus k in n implies m plus k plus 1 is in n.
So we're treating n plus k like it's a number.
Because maybe if I would have put parentheses there, that would have helped.
Because
Yeah.
the rule is, if there's a number in the inductive set, that number plus 1 is also in the set. Right?
Assume k is in A. What does that mean?
That number.
That means m plus k is a natural number. M plus k is a natural number. M plus k is a natural number.
Right. Okay.
Good? So m plus k is just our longhand way of writing some natural number.
And then now we can do 6.
And we're done. And then because you guys are using paper, you can't have this blank white space. Otherwise everyone on the internet will see how ugly your proof looks.
Yeah.
Alright. While you're writing that, really quick tell me what the next one is so I can...
So it's prove that the product mn also is a natural number.
Ah, same thing except for product.
Hint.
Okay.
Fix m and define the set n to be.
Yeah, I got it. You can continue writing.
I always forget to do my periods. So same thing.
Yep.
You should let us try to do it.
Oh, sure, go ahead.
Okay, I want to do them with them. And I want you to help if I'm screwed up. Let n be in the natural numbers and let A be the set of all natural, or let A be the set where n is in, no, where n is in the natural numbers. Right? Where n is in the natural numbers and are natural. And
Such that.
such that, that's how that means. Such that n times n is in the natural numbers.
Yeah, so read what that sentence to me real quick.
So let n be in the natural numbers and let A be the set of numbers that n is in the natural numbers and that
The
n times that number is.
Don't explain to me what it means. Read the statement to me.
Let n be in the natural numbers and let A be the set that n is in the natural numbers such that m times n is in the natural numbers.
Okay, almost. I just want to help you with your reading, because maybe that'll help you further. Let n be a natural number,
Let n be in the natural. Okay, that's why I said it.
right? Let n be a natural number, and let A equal the set of natural numbers such that m times n is in n. Let A be the set of natural numbers n such that m times n is in n.
Right.
So how does that prove it? If we can, well, what are we trying to show then?
Okay, we're trying to show that any n. Okay, we're trying to show.
n.
Think about this.
Oh, n, yeah.
Any n times m is another natural numbers. That proves that set. But why do we want to prove that set? We want to prove that that set is natural numbers.
So here's a big picture of what we want to do. Your space could say to me, look, give me any natural number m you want. And I'm going to show to you that I can multiply by any natural number and it's still a natural number.
Right, and I
So
do
here
this.
we're saying, give me any arbitrary natural number, call it n. Now I'm going to show you that I can take every natural number n, and their product is still a natural number.
Right, and so the way to do this is through induction, and then how you do that is prove that this set, which is my number that I'm timesing by,
Right.
is natural.
Is all the natural numbers. So you're going to prove that A, the set of all natural numbers that make the product a natural number, is all natural numbers. So if you can show that A is all natural numbers, then you're done.
Right.
Because A is all the things that we can multiply m by to get a natural number.
Right.
And if A is a set of all natural numbers, then we can multiply m by all natural numbers and still get a natural number.
Right. So observe that. Observe. Okay, I just want to say observe that n or 1 is in n. Right?
How do you want to show that one's in A?
Do you have to prove it by
Or
induction?
1's in A. Well, n's in A,
Yes.
and n's all natural numbers, and natural numbers is.
Hold on. A is a set of all natural numbers that makes this true.
Yeah.
Right?
Yeah.
So does 1 make this true?
Yes.
How do you know?
Because n times 1 is n, which is a natural number.
Oh, there you
Okay.
go.
How do I say that though? Okay, so
Okay,
Observe that m times 1 is equal to m is a natural number.
Can you not say that?
Yeah, that's perfect. Showing that 1 is in A. Okay. Now,
Now you assume k is in A.
uh-huh. What does it mean for K to be in A?
Then k plus 1 needs to be in A.
No, what does it mean for K to be in A?
Oh. That A equals.
M times K is in A.
Yeah.
M times K is a natural number, not an A. Right? A is a set of all natural numbers I can multiply
so
m by.
K is in A, which means
And
M
still get a
times
natural
K.
number.
So n times k is a natural number.
Yeah, that's what it means for K to be in A.
Where do I write that? So
Assume
that.
K is in A,
Such that.
Such that.
not such that,
So.
which
show me that.
means, or which implies, or however you want to say
That
it.
implies that.
Sure, if you want. That's my lazy way.
That's your other way.
That's my lazy way.
Oh, I like that.
Assume K is in A, which implies that what?
n times k is also a natural number.
Perfect. Now, what are we trying to show?
That the k plus 1 is in it.
What does that mean?
Okay, so multiplication is going to be different.
Slightly. So if you're stuck, then go do your bottom and work your way up, and maybe you'll see it.
Okay, what I'm thinking is k plus 1 is also a natural number. Has to be.
Yeah?
And then n times a natural number.
Is a natural number? That's what you're trying to prove.
Okay, so therefore.
Therefore, A is an inductive.
Therefore, A is inductive, or therefore n times n is
Okay.
n for all n.
How do I say it?
n.
Is inductive just move it?
However you want. I mean, he doesn't have to follow me verbatim.
Therefore, A is inductive.
What does that mean?
That means all of A is in the natural number, right? No, then k plus 1. See, how do you think like that?
What do I need to show in order to show that A is inductive? I need to show that K plus 1 is in A. Okay? And then when will we know that K plus 1 is in A?
When, okay, I got this. When n times k plus 1 is natural.
Perfect!
So, what do I say?
Then n times K plus 1 is in n. So you know that m times k is in n. You need to get that m times k plus 1 is in n. How on the blue moon are you going to do that?
Okay, so we know that in an inductive set, that if you have a number k plus 1, it's also in the inductive set.
Yeah, so I know m times k plus 1 is in n. one more then going up and distribute that. Maybe that would be the big key.
N
Yeah,
times
but
K
that,
plus M. Okay, and we have NK right there.
So how do we get from that to the other one? We need to add M, right?
Yeah.
So I know that M times K is a natural number. I know that M is a natural number. I know that M times K is a natural number. I need to show that N times K plus N is a natural number.
Okay, a natural number plus
Which we just did!
Hey! Okay, so for 4, we need to do, we know that, right?
Yeah, from the last theorem, or from
We know.
6a or whatever it was.
We know that a natural number plus is a natural number.
If you wrote that on a test, I would not give you credit for that, just so you know.
Therefore, why?
Because you're saying that the set of all natural numbers plus the set of all natural numbers
How do
is
you
the set of
say it?
natural numbers.
How do you say it?
Exactly the words you said out loud. We know that a natural number plus a natural number is a natural number. Or that the sum of two natural numbers is a natural number.
No.
Or you could have written it out exactly how we wrote it in the top statement of that.
Two
If m and n are natural, then m plus n is natural.
numbers.
Or if
Is two natural
the sum of two natural numbers.
Wait, I have to go natural.
Natural. Natural.
So, then, isn't it then?
If you wanna.
We know the sum of two natural numbers is natural. Then, m times k plus m. Oh, we gotta show this. Wait, we gotta show this.
We already showed that.
So I need to show.
No.
Okay.
Then m times k plus m is a sum of two natural numbers. And you're done.
Then
There you go. Easy. Oh my goodness. Could have done it in my sleep. Right? Okay, what's next?
Prove that if n is a natural number greater than 1, then n minus 1 is also a natural number.
Okay. Show that if n is a natural number where n is greater than 1, then what?
Prove that if n is a natural number greater than 1, then n minus 1 is also a natural number.
says int prove the set, and then such that n equals 1 or in the natural numbers n minus 1 in natural numbers is inductive.
Yeah, so here's how we're going to think about it. To show that this statement is true for all n greater than 1, which means what? It's true for 2, 3, 4, 5, 6, 7, 8, etc. Is the same thing as showing A. So we're making A the set of all the natural numbers that either make this true or 1.
Not 1.
This doesn't include 1 up here, right? So if we include 1 in A and show A is inductive, then we're done. So we're saying tag on 1 to A.
Okay, wait. So we're trying to show that A is the set of all natural numbers where n minus 1 is a natural number.
We're defining A to be the set of all natural numbers that make this statement true, and then also put 1 in there. And we're going to show that A is the set of all natural numbers.
Why do we put 1 in there?
So that we can show that A is inductive.
Okay, but if you put 1 in there, it now makes your thing false, doesn't it?
1 makes this statement. 1 doesn't work up here.
Yeah.
Right?
Yeah.
So we want A to be the set of everything that makes this true, and the natural numbers that didn't make it true. So that we can show that A is all natural numbers.
How do you make k plus 1?
But you just said there's going to be some natural numbers that doesn't make it true.
1 is the natural number that's not going to make it true. So we're saying, look, if we make A the set of all natural numbers that make it true, or 1, then A is going to be all natural numbers.
And then when we're done,
so all natural numbers that aren't 1 make this true. Because all natural numbers that make it true, or 1, is all natural numbers.
okay.
So here's another way to think about
I
A.
totally get you now.
A is equal to the set of all n in n,
No.
such that that is true. Unioned with the set containing 1.
Okay.
So here's what we're saying. We're saying to show that this is true for all natural numbers except 1, we're going to show that this set is all natural numbers. So take all the things that make it true, put 1 in there, and now you have all natural numbers. If I have a set of things, if I say secret set B, and you want to know what's in B, and here's what I tell you about B. I tell you that B union 1 is equal to the natural numbers. Then what do you know about B? It has to have 2, 3, 4, 5, 6, 7, 8, 9, 10. It has to have every natural number greater than 1. It might also have 1, but it has to have every natural number greater than 1.
Right.
Now we happen to know
That 1's going to be the only thing.
1 doesn't make this true, right? Because it's not greater than it. But, do you see the logic there? Okay. So that's why this weird statement. So that's the weirdness of the statement. But now we just need to show that A is inductive, right?
Yeah, if we prove A is inductive, we prove that. If n is a natural number, we're integrating.
So observe n is in 1, so n is in 8.
Now I have to do kind of two weird things here. So,
Why isn't this?
you'll see in my assumption.
1 is an A, and observe that 2 minus 1 is
A natural number.
Is 1, which is a natural number.
Which means 2 is an 8.
Because we know a number, or a natural number minus 1 is a natural number.
No, we know that 1 is a natural number. 2 minus 1 happens to be 1. So 2 minus 1 is a natural number.
Oh, because 1.
2 minus 1 is a natural number. Therefore 2 minus 1 is a natural number. Therefore 2 is an A. A is a set of all the things I can subtract 1 from and still get a natural number.
Okay, yeah.
You good there?
Yeah.
Now the reason that I need to show that 2 is an A is because I need to say, assume K in A where K is greater than 1 implies K plus 1 is in A where K plus 1 is greater than 1. Remember our statement is true for K, or for N greater than 1.
Yeah, if this was just N, you'd just say K. But
If I just show that 1's in there, I never know that there is some other K in there that could make the statement true. In other words, if I just show that 1's in there, for all I know, this is just equal to the set 1.
Okay.
Well, maybe I don't need to show the 2's in there. I do if I want to use this information. So I know there's at least one element in there greater than 1. Right? So now let K be another element in there greater than 1. Could be 2, could be anything. But it's greater than 1. And we need to get to K plus 1. Well, let's finish. What does it mean for K greater than 1 to be an A?
Then K plus 1 is greater than 1, which is an A.
Right? A is a set of all natural numbers I can subtract 1 from and get a natural number.
Right.
Or 1. But we know we're not talking about 1.
Right, we're talking about.
So if K is in A and K is not 1, remember, if you're in A, one of these two things is true.
Yep.
Either you're a natural number that you can subtract 1 from and get a natural number, or you're 1.
But you're
Okay.
not both.
Assume K is in A and it's greater than 1. So it's not this, in other words.
So it has to be that.
So then it had to have satisfied this statement. We know there's at least one element in there that does satisfy that statement. So
A lot.
I'm going to show you another way of doing this, where we just talk about a base case to avoid this.
Oh.
Because this is doing some this is not hand waving. This is making kind of a mess so that we can show that A is a set of all natural numbers. Instead of just showing that the statement is true for all natural numbers greater than 1. I'm going to show you how we would typically show that this is true for all natural numbers greater than 1. I'm going to do it the messy way, and then I'll redo the same proof the way it's commonly done. Good?
Yeah.
Okay.
And I'll walk you through the logic of it the second way. Okay. So assume K greater than 1 is in A. What does that mean? That means it had to satisfy this statement. So that means K minus 1 is a natural number, right?
Then what does that mean?
Where am I trying to get? Maybe let's go down to
No,
the
you
very
need to
bottom.
get K plus 1.
Huh?
Trying
No,
to
you need to get K plus 1.
I need to show that K plus 1 is an A.
Right.
So we'll come down here some. Then K plus 1 is an A. What does that mean?
Therefore, K is an A, or K is a natural number.
wait, why did you do that?
You can do that. You just put those two together. You just simplify this.
Oh, that's.
Okay, so I need to use this. K minus 1's in a natural number to show that K is a natural number.
Then you just plus 1.
Yeah! Since N is inductive,
Then any number.
K minus 1 in N implies K plus 1 minus 1 is in N, then k plus 1 is in A.
Since n is inductive.
Therefore,
I'm kind of stuck on 5.
okay.
Since n is inductive.
What does it mean to be an inductive set?
That number
It means
plus-
two things. It means 1's in the set, and it means if k is in the set, then k plus 1's in the set. Is this and n?
We're assuming it is.
Okay. So did we assume that this is in n?
Yeah.
So if this is in n, is this in n?
Okay, yeah, is in n.
So if this is in n, then this is in n?
No.
What does inductive mean? It means if k is in the set, then k plus 1's in the set.
K, but it's k minus 1.
It's just a variable. It's just some number.
Okay.
If some number is in the set, then that number plus 1's in the set. Here we have some number in the set. Then that number plus 1's in the set. Since n is inductive, it's a definition of being inductive. We know that the natural numbers are inductive. That's something we proved. So since the natural numbers are inductive, since the set of all natural numbers is inductive, that being in them implies that plus 1 is in them. So it means to be inductive. Take any element out of the set. If you add 1 to that element, you get another element in the set.
Okay.
Does that make sense?
Yeah.
So does the logic of the proof follow?
Yeah.
Okay, now let's do it a second way, in a way that kind of makes more sense. So let's not talk about an inductive set. We're going to talk about a secret set again, A. I'm going to tell you two things about A. I tell you that 2 is in A. And I tell you that k in A implies k plus 1 is in A. What do you know about A? What are the elements that has to be in A?
1. 1 has to be in A. Because k plus 1 is in A.
Let's start listing out elements that we know are in it. What's the first element that you know is in for sure?
2.
2. Okay, what else do you know is in there?
Okay.
3. What else do you know is in there?
4.
4. What else do you know is in there?
5.
5. What else do you know is in there?
6.
Do you know that one's in there?
No.
No, you don't know that one's in there. So notice that if you show that 2's in A, and that if k is in A, k plus 1's in A, then A has to be all the natural numbers greater than 1.
Yeah.
Okay? Notice that that's what this statement is saying is true for. So there's a different way that we could have done this. And this is the way it would have been done. Now, rather than proving all the time that a set is inductive, showing that 1's in A, and then that if k is in A, k plus 1's in A, rather than doing that all the time, we show that all the natural numbers starting at a specific natural number are in the set. So in this case, starting at 2. We call this the base case, the one that we want to start at. So I'm going to do the exact same proof the way that you'd probably see it if you went and looked at it online. So the top is proof if n is in n and n is greater than 1, comma, then n minus 1 is in n. Right?
Yeah.
1, base case. Observe that 2 minus 1 is equal to 1 is in n. Or in other words, the statement is true for 2. Assume the statement is true for k.
Yeah. Isn't this still proof by induction?
Yes, it is proof by induction.
I still don't get why R2 is important.
So let's stop for a second. Come back over here to our secret set. So our secret set A, I told you that 2 is in A, and I told you that if k is in A, then k plus 1 is in A, right? And you were able to tell me all these elements in it. Well, what if I just tell you this? A is a secret set, and if k is in A, k plus 1 is in A. Is there any reason why k couldn't be this set?
No.
So if we just show this, that doesn't tell us that much about our set A. It could have been that.
So
It could have been
our point in
the
saying
set of all natural numbers where n is greater than or equal to. We needed to show that this is true for all natural numbers greater than 1.
right.
In other words, starting at 2 and every natural number from then on, this statement's true. So show it's true for 2, and show if it's true for 2, then it's true for 3, and if it's true for 3, then it's true for 4. Or in other words, show it's true for 2, and then show if it's true for k, it's true for k plus 1. Well, that means it's going to be true for 2 and every natural number from then on. So this was the exact same thinking that we did over here. Just without using the set of natural numbers directly. So we said, look, 2 makes the statement true, and then if k makes the statement true, k plus 1 makes the statement true. Therefore, all natural numbers greater than 1 make the statement true. So this was the same thinking that we did. And here it's clear to see the thinking, I think, than over here. Here we're using that exact same type of thinking, but rather than saying it's true for all natural numbers greater than some natural number, we're going to say, make some set that we can make equal to the natural numbers, and make sure it includes all the bad ones. So showing that this is natural is the same thing as showing that the statement's true for all n greater than 1. You see that?
Mm-hmm.
You see how these two are using the same thinking?
Yeah.
And that's why we need the 2. The 2 is giving us this, where to start. Because we're basically saying let this A equal the union of 1 with this set right here. And we were showing that that gave us natural numbers. Okay, any questions on that?
No, I see.
I know it's kind of weird. We'll keep doing inductive proofs like this, but you'll get to the point where you feel comfortable doing it this way instead.
I don't know why, but that way feels better.
Because you're being very explicit this way about exactly what you're doing. Here we never make mention of that set A that we're using behind the scenes. We're assuming you're keeping up with that in your brain. You know how proof by induction works. Here's the base case. Here's our assumption for K. Here's how K plus 1's still in there. So it's really concise. But this walks you through exactly all the thinking that goes behind it. Okay. Now what?
Almost 11. Jeez.
What was the plan?
Do you finish chapter 2 and
Finish
start
chapter 1.
section 3?
Finish chapter 1 by going through section 1.2 and 1.3.
Oh,
Remember, we spent 2 weeks on preliminaries.
This is stupid, we need to get done.
Prove that if n and m are natural numbers such that n is greater than m, then n minus m is also a natural number.
Do you think you could do that one on your own now?
Prove that if n.
You're going to use the previous proof that we just did for your base case.
This one.
Yeah, so let me give you a quick outline of what that proof's going to look like. So we're proving if n and m are natural numbers such that n is greater than m, then n minus m is a natural number.
What if you just make m 1?
1, let m in n. 2,
And
then
wouldn't it be,
m minus 1 is an n.
wouldn't it be let n in n? Or let n be natural? N, not n.
Let m be a natural number.
Okay, then n minus
It
1.
need to be such that m is greater than 1. Oh, sorry. We're doing the n greater than. Is that what you were saying? So we'll pick an n, and then we'll do induction 1. Well, let me just change my order here. So we're saying pick a natural number.
There you go.
Then for every other natural number less than it,
There's another natural.
then their difference is a natural number. Okay? So pick m. Then m minus 1 is in n.
Right.
Right? So, which shows it works for 1.
Oh, does it? Wait, is 0 the natural number?
No. Alright, let's explicitly write it down.
1 minus 1 is not the natural number. Such that n minus n isn't the natural number. And n is greater than. No, we do not need to write that. M is greater than n.
m minus n. So now we're letting a be the set of all natural numbers that make that statement true. And then we're going to have to do a similar trick. Ooh, I don't like that. Is that right down here? No, I just did it that way. Alright, we'll just continue for now. Okay, let a be the set of all natural numbers such that m minus n is a natural number, right?
Okay.
So you let an n be at 1?
What does it mean for k to be an A?
K plus 1 is because A is a natural number. A is in the natural numbers.
Then k plus 1 is a natural number. That doesn't help us. If k is an A, what does that mean?
K minus 1 is an
K minus.
A. Or N minus K is an A.
N.
Right?
Yeah.
So now we need to show that k plus 1 is an A, right?
Yeah.
Almost. Remember that this statement is only true for all n less than n.
Yeah.
So we need to show that k plus 1
less
is
than
either
n.
an A or k plus 1 is equal to n. It's not less than it, right?
Okay.
Wait.
E
Trying to show that k plus 1 is n.
It's either M or it's less than N. I don't know why you're saying it's either N.
Yeah.
Oh, obviously. It can either be N because K, if K plus 1 is N, then K is less than N.
I'm still not seeing what it is.
So let's think about this for a specific set. So let's say m equals 4. Then A equals a set what?
1, 2, 3.
1, 2, 3. Right? I'm saying if you pick K to be 3, then is a statement going to be true for K plus 1?
Yeah.
No.
No. So,
Well,
one of two things is going to happen for your choices of K. Here's your 3 choices of K. If you pick this for K, then K plus 1's in there. If you pick this for K, K plus 1's in there. But if you pick this for K, K plus 1 is equal to M.
Which is 4.
Which we don't want. So we want the case where K plus 1 is less than M. So we want K to be less than M minus 1.
Oh.
Okay? So this only works for specific Ks. Right? So I probably should have said up here, maybe I want to change this. Using these sets is making a mess. Suit for m and n with n greater than m. Well, let me just write what I wrote and then we'll talk. Except I used n here. Suit for m and n with n greater than m. If m is greater than k plus 1, then we want to show it's true. So we're showing that k being in there implies k plus 1 is in there only if m was greater than k plus 1. Right? So these are our two options. K plus 1 is equal to m or k plus 1 is less than m.
right.
So we're going to show that k implies k plus 1. Let me write this more explicitly. We're going to show that k in A implies k plus 1 is in A for
All cases but.
k plus 1 less than m.
So what does that for mean?
When we're saying that this implication is only true when k plus 1 is less than m.
Right.
Right? Because we're not going to show that A is true for all natural numbers. It's true for all natural numbers up to a certain natural number. It's true for all natural numbers up to
when k plus 1 is less than
k plus 1 less than m. So let's look at the statement one more time. We're showing that for all natural numbers less than m, this difference is in n. Right? So we need a limit as high as we can go to n. So the max natural number that we're talking about needs to be less than m to make sure that statement's true.
Yeah.
So let k in A, maybe here's how to write it. Let k in A where k plus 1 is less than m. Right? Then what? So if k is in A, then m minus k is in n. That's what it means for k to be in A, right? Then
plus 1 is in n. Or is in A? M minus k is an actual number. Right. Therefore, A is inductive.
no, it's not inductive.
Yeah, it is.
No, we showed it would be inductive if we also unioned onto here. So we can say let A equal the set of all n that make this true, unioned with the set of all natural numbers such that n is greater than or equal to n. And then we could show that that was inductive.
So is that the proof?
Yeah.
We're done after we prove that A contains all natural numbers less than n.
Yeah, that's what we want to show. A is the set of all things that make the statement true. And we're showing that this statement is true for all n less than m.
Right.
So maybe we should have wrote A a little bit different. Let A equal the set of all natural numbers in n such that n is less than m and n minus m is in n. Maybe that's the way we should start that.
Yeah.
Right?
Mm-hmm.
And then we show ones in there. And then we show if k is in there and k is not the last element, k plus 1's in there. Right?
Yeah.
Because this could potentially only contain one element. Right? If m's 2, then this just contains 1.
Right.
Okay. What number was that?
8.
8. So the 9 has you go through some proofs with the integers. Only do part A for 9. Don't worry about the rest.
So just prove the sum.
Yeah, just prove that the sum of integers is an integer. Now that's going to be real close to showing that the sum of naturals is a natural, but you have to worry about 2 other cases.
What cases? Oh.
Well, you need to worry about 4 cases. You're going to have 4 cases in there. Right? Let's go over what the 4 cases are real quick. Two of them are really the same case, but let's go over how you would prove that. So the way that you prove that is, you start out with m and n are integers, right? And you need to show that m plus n is an integer. There's 4 cases. It could be that n is a natural number and n is a natural number, in which case there's some, we already did. It could be negative n is a natural number and n is a natural number.
Wait, what is z rational?
Z, integers. All the whole numbers, including 0, positive, negative.
Negative n can't be, or negatives can't be natural, I thought.
So maybe we need to go over the definition of integers one more time. Actually, there's one more case where if m or n is 0, let's handle this case real quick so that you know we're out the door. So I want to show that n plus n is an integer, right?
Yeah.
And I want to show that's true no matter what integers those are. Well, first off, if one of those 2 integers is 0, you're done.
Right.
Right? Because n plus 0 is just
Natural
n,
number.
which we already know is an
And
integer.
natural number.
Or 0 plus n is just n, which we already know is an integer. So this case is real easy. So these are the 4 cases that you kind of have to break down, and these 2 cases are really the same case. One of them is positive, one of them is negative. Now maybe you're confused about this positive and negative, so let's write out the definition of
It's
an
just a
integer.
negative natural number.
What is a set of all integers?
It's a set of any natural number over
It's a
another
set of
natural
all x such that
number. Any natural
x is a natural number, or x is equal to 0, or negative x is a natural number.
These are what numbers?
This is the definition of integers.
Integers. There we go.
So what are the integers, first of all? Negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, 6.
Okay.
That's the integers, right? So let's make sure that this makes sense. So let's test some things and see if it's in there. Is 9 in there?
Yeah.
Well, let's see. Does 9 satisfy one of these?
Yeah.
Yeah, 9's a natural number. Is 0 in there?
Yeah.
Yeah, 0's in there. Is negative 13 in there?
Yeah.
Well, is negative 13 a natural number? Okay, the negative 13's in there. You see how this captures the idea of all natural numbers?
Yeah.
Or all integers? And you just really proved a bunch of stuff about natural numbers. So you want to talk about integers in terms of natural numbers. So if you have 2 integers, you know that one of these 4 cases is true, ignoring the case where there's zeros. That's easy, right? If you have 2 integers, m and n, then either they're both natural numbers, or the negative of one of them is a natural number, or the negatives of both of them is a natural number. Right?
Right.
So you need to show, in this case, this sum's a natural number. You need to show in this case the sum's a natural number. And you need to show in this case the sum's a natural number. Or an integer, I mean.
Interesting. Okay, I was like,
Right. So I need to show the fact that negative m plus negative n is a natural number, thinking about this case. Showing that this is a natural number.
integer, you mean?
Well, no. I know that that's natural, and I know that that's natural, right? So I know that their sum's a natural using our last proofs. Here's some information I can use. And I need to somehow use that to show that m plus n is in Z.
It kind of feels like it's self-explanatory. Like it just feels obvious.
Well, how do you show that m plus n is in Z? There's 3 ways to do it. You show that m plus n is a natural number, or you show that m plus n is 0, or you show that m plus n, it's negative, is a natural number. In this case, you're going to show that the negative of this is a natural number. therefore that's in Z.
Right, I see.
So you're going to go from this to negative m plus n is a natural to m plus n is in Z.
I see. Okay.
That's the type of thing you can use. So I'm going to leave that last one for you.
Okay.
And you don't have to go through all of them if you don't want. You can just do A. Maybe if you feel like you need to do more, do more. Because it's just going to have you do what we just really did for show that the sum of integers is integers, show that the product of integers is integers, and show that the difference of integers is integers.
So we won't be using.
And it's kind of apply the same thinking over and over again using what we did with natural numbers.
What number 9 we would be using inductive?
These are still going to be proved by induction. You're going to pick some integer n, and then pick some other integer n. Right?
And show that their sum is irrational.
Is an integer.
Or is an integer?
Oh, no, these aren't going to be proved by induction.
It
Sorry.
feels like
It's going to fall from the inductive proofs we've already done on the natural numbers. If you were to not use what you already proved on the natural numbers, then you would do proof by induction. So if you start from scratch, yes, you'll do proof by induction. If you don't, then you won't. All right.
So we'll use the things we just already proved to prove it.
Yeah.
Okay.
Because the integers can be defined in terms of naturals, and we already proved lots of things about naturals. Remember, use the definition. What's the definition of an integer?
It's the set containing 1, 2, 3.
All the natural numbers, or 0, or the negatives of the natural
Oh,
numbers.
integers, yes.
Yeah, that's what the integers are. Okay. So let's begin section 1.2. And we're gonna, so section 1.2, there's two big ideas that we want to prove in there. We want to prove, we want to show how dense the integers are in the real numbers and how dense the rationals are in the real numbers. So in other words, here's my real number line, right? 0, 1, 2, 3, -2, etc., right? Here's a real number line. And I say, is it possible for me to pick an interval right there that doesn't contain any integers?
No.
Integers.
Yeah.
Integers?
Integers.
Yeah. You're just dealing with rationals.
Yeah, it's possible to not get any integers there.
Or not rationals, real numbers.
-2's not in there, -1's not in there.
Right.
What integers are in there?
No.
None. So, the next question is, what about rationals? Is it possible for me to make an interval so small that the only thing it contains are irrationals
No.
and no rationals?
No.
Are you sure?
You can't make an interval encompass one number. You can't make an interval be so small it encompasses only one number. Don't you think?
Well, so it encompasses only one number, fine. But can it encompass an infinite number of irrationals? I mean, do the rationals, irrationals alternate? Does it go rational, irrational, rational, irrational, rational,
No,
irrational?
irrational.
So can't I just get a small little subset where everything in there is just irrationals? And there's no rationals?
Yeah, if
Yeah.
in theory, if you can encompass one number, but you can't do that.
No, I'm saying infinitely many though.
Oh,
Just really, really, really small. So even though it has an infinite number of elements, they all are irrational. The same way that I can start with an interval, right? Here's my interval. It contains 3 integers. But it's possible for me to keep zooming in, zooming in, zooming in, zooming in to the point where I don't contain any integers, right? Is it possible for me to do that same thing with rationals?
I don't know.
Zoom in, zoom in, zoom in to the point where you can't get any rationals. The answer is no, and we're going to prove it. So 2 big ideas we're going to prove. One, the rationals are dense in R is what we mean by that. We mean no matter how small of an interval of R you take, you'll always have an infinite number of rational numbers, or at least one rational. And then 2, we're going to show that if you take any interval of the form C plus 1, that always contains at least one integer. So if I start, for example, at 2.917, and I go to 3.917, I'm guaranteed that there's one integer in there. And in this case, it's obviously 3. You understand?
No, I don't understand.
Does the interval from here to here contain an integer?
Yeah.
So pick any real number C. Well, notice it includes on this side and is open on this side. So pick any real number C. Then from C including C to C plus 1 always includes one integer. So those are the 2 big theorems that we're going to prove. And we're going to work with stuff to get up to proving these things. Does that make sense? First thing we need to prove is what's called the Archimedean property. This is also something that we covered in geometry. The Archimedean property is prove that, I'll just say given any positive number C, pick C however you want, there exists some natural number in n such that n is greater than C.
Now are we still going to be doing proof by induction?
Not on this one. Proof by induction will come up over and over again as we go throughout the class. Okay, but do you understand what this is saying? We're saying that there isn't any maximum natural number. For any massive number you pick, I can always find a natural number bigger than that massive number. Okay, that's what we're going to prove.
I feel like we already proved that defining the natural numbers.
No, you just think intuitively in your head, I can keep making it bigger and bigger and bigger.
Well, you have n plus 1.
That's what I'm saying.
Yeah,
Right.
doesn't that prove it?
So now let's prove it. Using the fact that we know that the natural numbers are inductive. Right? Assume, by way of contradiction, that there exists B in R such that B is greater than or equal to n for all n, not greater than or equal, but greater than n, for all n in n. In other words, assume that there is some real number that's so massive it's bigger than every natural number. Assume by way of contradiction. We're going to show this is impossible. Right? 2. Then n is bounded from above, right? That's what it means. Then n is bounded from above, comma, and the supremum of n exists, equal to, what we call C.
Not C, because we used to.
Okay? So if n is bounded from above, then it has to have a supremum, a least upper bound. That was our completeness axiom. Every non-empty set of real numbers that's bounded from above has a least upper bound, a supremum d. So d is the supremum of n. 4, because we don't like 3. Then d minus 1/2 is less than d is not an upper bound. Right? If d is the least upper bound, d minus 1/2 is not an upper bound. 4. Then there exists some n in n such that n is greater than d minus 1/2. Right? If d is not an upper bound, then that means there's an element of the set greater than it. Right?
But D is the upper bound. So
Sorry, d minus 1/2 is not an upper bound. D is the least upper bound. Right? That means anything smaller than d is not an upper bound.
Right.
Is d minus 1/2 smaller than d?
Yes.
Yeah.
So it's not an upper bound.
Right.
So there is an element in the set greater than d minus 1/2.
In the set of
Look.
natural numbers.
Here's my set. 1, 2, 3, 4. What's the supremum of that?
4.
4. So is 4 minus 1/2 an upper bound of that?
No.
No! Which means that there's an element in there, namely 4, greater than that.
Okay.
That's what we're saying.
Oh.
We're saying since this is less than our least upper bound, then it's not an upper bound. Which means that there is some element in the set, then there exists n in our set that we're talking about, such that n is greater than that number, because it's not an upper bound.
Okay.
That's what it means to not be an upper bound. It's not greater than all the elements in the set. So there is an element in the set greater than it.
Right.
Yeah.
And n plus 1 is greater than d plus 1/2 is greater than d.
Right.
Contradiction. We found an element in n greater than our supremum.
I see. It's exactly
So
what
we took this, we added 1 to both sides, and we got this. Right?
Yeah.
And so n plus 1 is greater than d. So we found some natural number bigger than our supremum. That's impossible.
Right.
So d didn't actually exist. So either the set of natural numbers is empty, or it's not bounded. We know it's not empty, so it can't be bounded. Good?
Yeah.
Okay, that's called the Archimedean property. So now you can use this. For any real number you pick, or for any real number I give you, you can always find a natural number bigger than it.
Right.
There's a corollary to this, which you're going to use all the time. And Jacob might remember this from real basic calculus proofs. Given epsilon in the positive real numbers, we usually use epsilon to represent a really, really, really small number. So given a really, really small positive number, there exists some natural number such that 1 over that natural number is less than epsilon.
Oh, so it's kind of like the opposite. of
Yeah.
what we just did.
Yeah. So, 1. Observe.
We're basically proving that there's an infinite amount of rational numbers
No.
between two natural numbers.
What are we proving?
No.
That is what it feels like we just did.
No. We first proved no matter how big of a real number you pick, I can find a natural number bigger than it.
Yeah.
Now I'm going to show you that no matter how small of a real number you pick, I can find a number smaller than it.
Yeah.
So all I'm showing is that I can find a number smaller than you, and I can always find a number bigger than you.
Okay.
That's what I'm showing. So observe that. Let's see, 1 over epsilon is a positive real number.
Donnie, real quick. Last time you showed that you can always find an integer bigger. This time you're not dealing with integers. Is that right? Or sorry, you showed that you can show a natural number bigger.
Which is a number.
Okay.
This happens to be a natural number. And this happens to be a rational number, smaller than any number you pick. But doesn't matter. So observe that 1 divided by a positive number is a positive number, right? How do we know that?
It's a 1 over.
We showed that if A is positive, A inverse is positive.
Yeah.
So if epsilon is positive, epsilon inverse is positive. Which means that, which is 1 times epsilon, that is positive times positive. Right? Yeah, those epsilons are terrible, but you get the point. Okay. 2. By the Archimedean property, then there exists n in n such that n is greater than 1 over epsilon. Right? Which, a little bit of algebra, gives you 1 over n is less than epsilon. Multiply both sides by epsilon, divide both sides by the natural by n. You know, we're done.
That's cool.
So for any teeny tiny number you pick, I can find 1 over n such that it's smaller than that teeny tiny number you pick. Another way we can say that is we prove that there is no smallest positive real number.
Right.
You can't find the smallest positive real number. No matter how small a positive real number you find, I can find one smaller.
This is calculus.
Yeah, that's what this whole class is.
Yeah, I know.
Can you,
It's the analysis of the real numbers.
class, explain to me what calculus is?
It's the analysis of the real numbers. So in discrete math, what we were basically doing is analysis of integers. All the sets that we were talking about were either the integers or subsets of integers.
Calculus. So what he did was just
He did
Showing
an
what-
analysis of the real numbers. He did an analysis of the things that you could claim about the real numbers.
Literally,
Now, there's three main ideas that you're very interested in calculus. You're interested in the idea of a limit, which is what a sequence approaches,
this is
kind of like a supremum.
this is close to well, yeah, it's getting.
Two of the major applications of calculus are if you have some function, you can find the slope of a function at any point, and you can find the area under the function. Those are two main ideas that are applications of the derivative and the integral, but the derivative and the integral go well beyond these two basic applications. These are just two very, very basic applications that Jacob most likely focused on in his
You
class.
can find a formula for that line where any x you plug in, it comes out to the slope of that x.
We'll get to it when we get to it.
I've just always wondered, like, I'm in calculus and people say, so what do you do in calculus?
An analysis of the real
Real
numbers. We prove what can be proven about the sets of real numbers and functions from the real numbers to the real numbers. And then in topology, you do an analysis on just kind of sets in general. And you're interested particularly in continuous function sets. But we'll figure out what it means for a function to be continuous in calculus. The idea of a continuous function in calculus, if you have intuition for it, is basically a function that doesn't have any gaps. It goes like this. There's continuous, here's not continuous. But then the question is there an idea of a continuous function from the set 1, 2, 3 to the set square, triangle, smiley face? Is it possible for me to make a continuous function from this set to this set? And topology is interested in those types of questions. And yes, there is a way to make a continuous function from this set to this set. And our idea of continuous in calculus is just a special case of our continuous functions in topology. And so,
Donnie, at 10 to, I have to go talk to Susan for 2 seconds. Or anywhere from then to 10 to.
well, I'll just excuse it, 10 to. Okay. So, that's the Archimedean property. Next, we're going to prove as the Archimedean property and a counterpart to the Archimedean property. So now you can use those two things. Next, we're going to prove given n in n, n to n plus 1 does not contain a natural number. That interval. Does that make sense? Or does not contain an integer?
Two can argue to finish this.
Oh, for all n and z. Okay, that's why I think confused. Okay, so here's what we're showing. Pick an integer, -7. Now we're saying the interval -7 to -6 does not contain an integer. Okay?
Right.
You understand what we're trying to prove?
Right.
Okay, we're going to prove a special case first. We're first going to prove that 0 to 1 does not contain an integer.
Wait, what does the z mean again?
The set of all integers.
Okay.
One. Observe that
0.
the set of all positive integers is n. Right? The natural numbers is a set of all positive integers. And that the smallest natural number is 1. Right? 2. interval 0 to 1 does not contain an integer. So look, is the interval 0 to 1 always positive?
Yeah.
And all the positive integers are natural numbers?
Yeah.
And the smallest positive integer is 1?
And the smallest positive natural is 1.
Which is also the smallest positive integer. All the positive integers are natural numbers.
Yeah.
So the smallest natural number and the smallest positive integer are the same thing.
Yeah.
So, this is only positive numbers, and it doesn't contain 1. It only contains elements less than 1. Right?
Mm-hmm.
So there is no integer in there.
Mm-hmm.
You good with that logic?
Yeah.
Okay. 3. So we're going to use this little side fact to disprove the statement in general. So assume, by way of contradiction, that there exists some integer k such that k is in the interval n to n plus 1. So assume that n plus 1 contains an integer called k, right? And this is by way of contradiction, it's impossible. Then what does that mean? That means n is less than k is less than n plus 1. Right?
Yeah.
Which gives us that 0 is less than k minus n is less than 1. Subtracting n.
Right.
Subtract n from that gives us 0. Subtract n from that gives us k minus n. Subtract n from that gives us 1.
Why are you subtracting n?
Well, now look at it. K minus n is between 0 and 1. That's the same thing as k minus n is in the interval 0 to 1.
Right.
I just found an integer. I just really showed that if k is in here, then k minus n is in here, which we know is impossible.
Right.
So this is impossible.
Right.
Good?
That was a different, by the way. Oh, we just, okay. Yeah.
How do you know?
Does not contain an integer. And we're done, right?
Yeah.
Okay, that was that. Now let's do the next one.
So we're proving like theorems that we can use, or what?
Yeah, all these things are going to work up to proving those two major theorems I told you at the beginning. So now the next little theorem that we're going to use is a non-empty set of integers bounded from above has a max element. Now remember in your homework, you were asked true or false. Does every non-empty set of real numbers have a max element? And you said no. And the example you gave was the interval 0 to 1.
Yeah.
Right?
Yeah. Well,
You remember that?
We did like 1 to 7.
Whatever it was.
Yeah.
So you did some open interval and you said, here's an example of real numbers that doesn't contain a max element.
Yes.
Now we're going to prove that if it's just a set of integers, it does have a max element.
Just integers?
Yeah, if the only thing in there is integers, it does have a max element. Given A is a subset of Z, so A is a set of integers where it's not equal to the empty set, so it has something in there. Maybe I'll say A, or if A is a subset of integers not equal to the empty set, then A has a max element, or member. You understand what we're trying to prove?
Base member in the rationals. Is that rational?
No, integers.
Oh shoot, bounded from above. right? It can only have a max element if it's bounded from above. If A is a subset of integers bounded from above, let's just write this. If A is a subset of integers bounded from above, and it's not empty, and it's not equal to the empty set, then A has a max element.
Is it MP7 bounded from above?
Well, think about the integers in general. What's the max integer?
Nothing.
Right, you need it bounded from above. Then it's going to have a max.
Right. So a non-empty set.
So if it's a non-empty set and it's bounded from above,
Okay.
right? I guess we don't need to say non-empty because it can only be bounded from above if it's not empty.
Then A has max.
Oh well. So, 1, let A be as described up there. Good? 2, since it's bounded from above, then what?
Then it has a max element.
Well, then it has a supremum.
Supremum.
Wait, what if A?
What's the difference between a supremum and a max?
That interval has a supremum of 1. It doesn't have a max element. There's not a biggest thing inside of there. Anything you pick in here, I can find something bigger.
I thought that was our proof. Okay, last time we were proving what? In our homework, what were we proving?
I don't know what.
You're talking about that empty, or I thought
This
the question was.
exact thing. We proved that does not have a max element or a.
We proved that had a supremum. I thought we proved.
We
that.
didn't prove it has a supremum. That was our last axiom. Every non-empty set of integer or of real numbers bounded from above has a least upper bound or a supremum. So the least upper bound or supremum of this is 1, right?
But that.
But
But 1's not in there,
Oh.
so it's not a max element in there.
Yeah.
So in our homework we're dealing with max elements. Okay.
So, Donnie, I have a question. How come A can't be Z?
It could be. Well, because it has to be bounded from above. And Z isn't bounded from above. We just showed that the natural numbers aren't bounded from above by the Archimedean property.
Yeah.
So the integers can't be bounded from above. The natural numbers are a subset of that. So good so far?
Good.
So we know that this thing is bounded from above. We know it's not empty, therefore it has a supremum. So whatever its supremum is, we're going to call it A. And since A is a supremum, and observe
A is in.
that there exists n in A such that A minus 1 is less than n. So since A's, first off, the thing has a supremum, we're calling it A, which is its least upper bound, which means A minus 1 is not a least upper bound.
Right.
So it's not an upper bound at all. So there is some element m in A greater than A minus 1. A minus 1. A minus 1 is not an upper bound. This is the smallest upper bound. Anything smaller is not an upper bound, namely A minus 1.
Right.
So there has to be some element m greater than A minus 1.
Yeah, A.
A isn't necessarily an element of
Oh.
A. A is just a supremum. Just like the interval 0 to 1, the supremum of that was 1, but 1's not in that interval.
Right.
But it doesn't have a max element in that interval.
Right. We don't know if this has a max element either yet. We're trying to prove it does.
Right. There's just a number between A and
Yeah.
the number lower than 1 of A.
Right. There has to be, if A is the least upper bound, then there has to be some element in the set between A minus 1 and A. We're calling that the n. With me so far?
Yeah.
Alright. Then, how do I want to say that? Well, I'll just write the whole thing. Did I put the plus one on the other side? Yeah, I did. How can I make this make sense? It's like combining two things. Maybe I'll just write both things. You follow that?
Yeah. Plus one to both sides.
So this is true because A is a supremum, right? And then this is true from that. And then plus one to both sides of this gives me the right hand side of the inequality, and then this part of the inequality is right there.
Right, just because A.
All right. Now make sure you understand that.
Because it's only bounded from above.
Since it's bounded from above,
Does that imply it's not bounded from below?
not necessarily, but remember we're saying A is a subset of C,
Oh, yeah, true.
right? So everything in A has to be in there. Because everything in A has to be less than m plus 1. And we know that A is a set of integers, right? So, now from our proof last time, pick an integer. The open interval from that integer to that integer plus 1 does not contain any integers.
Okay.
So the interval m to m plus 1 does not contain any integers.
So M is that max element?
Yeah, in short, m is the max element, which is equal to a.
Wait, but I thought A was the biggest element.
Yeah, a and m happen to be the same thing in this.
Oh, okay, I think I get it.
Right? So here's what we said. This thing has to have a supremum, call it A, and there has to be some element in it, m, greater than a minus 1. Right? So we know that m is less than or equal to a is less than m plus 1. Now really, what we picked is m is equal to a. We just don't realize that yet. So you're good here, right?
Yeah.
So, since a is a supremum, and m is less than or equal to a, all the members are definitely less than m plus 1.
Right.
Right? So m plus 1 is for sure an upper bound. So this thing is whatever a is definitely a subset of this. Now, since the interval m to m plus 1 doesn't contain any integers, and a is just integers, we can get rid of the interval m to m plus 1, which just leaves us with this. Do you see what I did from here to here? Because that's the weirdest part. And then m, we already know is in a. So m is a supremum and is the max element.
Okay, so what do we prove?
That if a is a subset of integers bounded from above as a max element, and in short that max element is its supremum. Good? Okay. So now we're ready for
But that's
the final proof about integers.
like odds too.
Huh?
Obviously, right? Because integers, a set of integers, any set of integers has to have a max.
Not any set of integers.
Give me a set that's not.
The natural numbers. You just presently prove they don't have a max. That was called the Archimedean property.
Oh, sorry. Any set of integers bounded above. obviously has to have an S.
Well, yeah, I just proved it.
Yeah, obviously.
Obviously, I just proved it.
See, this is how.
You need to be careful about what you say is obvious. This is always worth noting over and over again. Far greater minds than yours or mine said a lot of things were obvious that turned out to be false. Give you one example. You know who Leibniz is?
No.
He's the one that helped invent calculus. Yeah, Newton and Leibniz invented calculus.
Okay.
You remember the product rule for taking a derivative?
Maybe.
The derivative of the first multiplied by the second plus the derivative of the second multiplied by the first.
Oh, yeah.
So if we take the derivative, if we have the function fg, and we take its derivative, that's equal to f prime times g plus g prime times f, right?
Yeah.
Newton had it in his notes for 10 days. We have it recorded in his journal. 10 days. It lasted in his journal. Obviously, that was in his notes for 10 days. There's an example of a far greater mind than yours or mine claiming that a false statement is obviously true. And there's other examples, but they just are about math that you and I aren't familiar with. Ramanujan, he was a guy from India, grew up in poverty, poor little Indian kid, and he happened to come across just a really basic algebra textbook. And he went through that basic algebra textbook, and from that he started deriving all this mathematics that the Western world already knew about. Some guy in the West found out about it, he's like, holy crap kid, let's get you up to date and have you start working on stuff. So they got him up to date and he started working on stuff. He started doing amazing things, but there was one holdup. They said, you gotta slow down, you gotta prove these things. You can't just say this is true and this is true, so this is true, and continue on your merry way. You gotta prove all these things are true. Because it was just obvious to him until one of the mathematicians that worked with him took a ton of time to find a counterexample to one of the things he thought was obvious. Like, that's why you need to prove. Because he didn't want to waste his time proving. He thought it was a waste of his time. He wanted to just move on with the world, push mathematics forward, not waste his time proving all these little things that he was happening to use. Turns out some of those things weren't true. Another great example is Tesla. Tesla is the one that's famous for trying to send electricity through the air. He spent a lot of time and effort in this. He's also the one that did alternating current. AC current. Not AC current, alternating current. AC. And he just had a great intuitive mind. In his mind, it was just intuitive. It just worked. He went, he did it. It worked. Amazing. He beat, you might know a little bit about him versus Thomas Edison. Thomas Edison wanted to use direct current. He wanted to use alternating current for their first power plants that they were putting in over by Niagara Falls. Anyways, so they had their two competing ideas. Alternating current works way better than direct current for long distance sending electricity. And it was through his intuition that he realized that, and he proved it, and we use it, and that's awesome. And he also had this intuition about how electricity should be sent through the air. And he spent so much of his life and so many resources trying to do this thing when what he was trying to do wasn't really possible. And if he would have just sat down and to do the math and prove his concept out, he would have saw what he should expect. He essentially invented the radio before it was invented. And if he would have sat down to the math, he might have realized, I just invented the radio. I just found a way to send information. He was so focused on sending a current that it was sending photons. They just weren't as much as he was expecting. But it was enough that it was radio. He essentially invented radio. He never realized it. Because he spent so much time, effort, and energy into this thing that he was convinced was possible to do that wasn't possible to do. And if he would have sat down and did the math to try and prove his concept before he did it, he would have realized that, which is too bad because he was a great mind. He spent a lot of time on that. From Tesla, there's all sorts of crazy stories people tell about him. And he secretly did it, and the government doesn't want you to know, blah, 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 weird stuff. But no, what he was trying to do was well. So, you need, lesson is, what you think is obvious, far greater minds have said things are obvious that it wasn't obvious. And so, it's always good to see if you can prove it. Because if it's obvious, proving it should be straightforward, right? Okay. Ooh, don't know if we're going to be able to get through this. I have 3 more proofs to do.
We got 5 minutes.
Well, so I'm going to talk to you for 2 seconds, then we can.
We'll just call it there, and we'll refresh next time. Because I don't want to rush through this next one, and it's fairly lengthy proof, because it's one of the two things that we were going over. So maybe just recap the theorems that we went over real quick to make sure you understand them. So, 1, we found out, given some positive number C in R, there exists a natural number such that n is greater than C. Right? Archimedean property. 2 was a corollary to that. Given epsilon in R plus, there exists some natural number such that 1 over n is smaller than epsilon. 3, we prove that given some integer,
There's no integer.
given that the interval does not contain an integer, and then we showed that, right? That was 4, is that one. Next, what we're going to show, 5, is that given any real number, contains 1 integer. Then we're going to show,
Obviously.
we're going to show that the rationals are dense in R, or in other words, given some interval AB, there exists little q in big Q such that little q is in that interval.
Oh, so we're finally going to prove that
Between any two real numbers you pick, there is a rational number, which means that the rationals are dense in R. That's how we say that. And then the last thing we're going to prove is
Real number.
there's just an irrational number such that Q is in AB.
There's no way that's true.
So the rationals and the irrationals are both dense in R. Pick any small little interval you want. It contains a rational number and also contains an irrational number.
I don't believe that.
Well, we'll prove it. So that's what we'll do next time, and we can call it there.
What do you want us to finish our homework?
Yeah, finish your homework, get it turned in to me,
We have
and
that
you can
class.
start the homework for next time as well.